All right, compound inequalities. Linear inequalities tend to have an infinite amount of values for the replacement variable. So that's why we always draw an arrow in one direction. So consider the following compound, meaning more than one, inequality statements. Determine the truth value of both inequalities, then determine the overall truth value. So 7 is more than 3, and 2 is less than 10. Well, both of those are true. So since this one is true and this one is true, then overall it is true. Look at the next one. 5 is less than 10. Is that true? Yes. And 11 is more than 20. Well, that's false. So overall, because it has the word and in the middle, both of them have to true, so overall, it's false. Next one. -4 is less than 7, and 8 is not less than 2, but it has the word or, so that means only one of them has to be true. So overall, this statement is true. 3 is more than 6, that's false. 8 is less than 5, that's false. Even though this says or, neither of them are true. So overall, it is false. Most students would correctly judge the truth values of the 4 examples above correctly, but there is a strange disconnect in math between the use of the word or and the way it is used in the real world. The next exercise will clarify this. All right, consider the compound inequality. Determine the truth value of each of the inequalities in the compound. So 8 is more than 2, or 3 is less than 10. Well, both of these are true, but there is the word or in it. So what does your intuition tell you the truth value of the compound statement is? What is the mathematical truth value? So the English version of that says that just one of them has to be true. So the intuition would mean one or the other. So you would know that because of the word or, it's false, but the mathematical truth is that it's true because only one of them has to be true in order for the overall to be true. The only way an or will be false is if all parts are false. So which of the following compound inequalities is false? Explain your reasoning. So 5 is more than 2, 4 is less than 1. 10 is more than 0, -3 is less than 10. -6 is less than 5, 7 is more than or equal to 7. -2 is less than or equal to 4, and 5 is more than 7. So looking at this, I have the word or. Remember, only one of them has to be true in order for the entire thing to be true. So this one is not false. That one is true. Again, only one of them has to be true, so it's not that one. With and, both have to be true, which both of those are. And this one is and one of them is false, so that one is false overall. A compound statement will be true only if all, so if it has the word and, all has to be true, or at least one of them has to be true. So now we can start to judge the truth values of inequalities that involve algebraic expressions and replacement values. Don't ever forget that a value of a variable is in the solution set of an equation or inequality if it makes it true and is not in the solution if it's false. Determine each of the following values is a solution set. So is 2 part of the solution set? So is 2 more than -3 and is 2 less than 5? So is 2 more than -3? Yes. Is 2 less than 5? Yes. Since it's an and, then this one is true. Yes, this one works. So -4. So is -4 less than or equal to -4? Is -4 more than 0? So first one, Negative 4 is less than or equal to 4. It is not more than 0, but it's an or. So overall, yes, it's true. It's part of the solution set. So 1. 3 times 1 plus 8 is more than 9. And then negative 2 times 1 plus 10 is less than 7. So we have to solve. 3 times 1 is 3 plus 8, is that more than 9? Is 11 more than 9? And negative 2 plus 10, is that less than 7? Is 8 less than 7? So it's true for this one, false for this one, but it's an and, so it's false. Next one, we're plugging 5 in. So 2 times 5 minus 1, is that less than 3? And is 5 plus 7 divided by 2 equal to 6? So 2 times 5 is 10, minus 1, is that less than 3? Is 9 less than 3? And 5 plus 7 is 12, divided by 2. Does 6 equal 6? So this one is false, this one is true, but it's or, so overall it's true because just one of them has to be true. We would also like to be able to produce number line graphs of compound inequalities. For now, we will stick with a few simple ones. So we're going to shade all values of x that are in the solution set. So x is less than 7 and x is more than or equal to negative 2. So we need to think of something that's less than 7 but more than negative 2. Well, 6 is less than 7 and more than negative 2. 3 and 0. All of those are true. So if I have 6 is on there, 3 is on there, and 0 is on there. We know that negative 2 is also on there because of the or equal to, but 7 is not. So it's going to be an open circle on 7, a closed circle on negative 2, and everything in between them. All right, this one is or. So x is more than or equal to 5. So it can be 5, 6. Or it's less than negative 1, so it can be negative 2. So we're going to have an open circle on negative 1 because it does not include negative 1, but it can include everything on the left side of it. And a closed circle on 5 because it's or equal to, and everything larger than 5. So you'll notice for and, it's everything that they have together. For or, it's everything that they have other than what is not listed. So this middle section here is not listed.